AcePhysics.org, Physics and Math Tutoring with Dr. H. In this presentation, I'll be discussing three conceptual problems involving direct current circuits in both series and parallel combinations. This is the first example problem. In the below two circuit diagrams, resistor R1 is greater than resistor R2. For both circuits, which resistor R1 or R2 dissipates the most power? This is a series circuit combination. There's a battery. The battery causes current to flow within the circuit. The current will flow clockwise. Charge carriers will move from the positive terminal of the battery through the resistor 1 through the resistor 2, and that's what's happening. The battery has chemical potential energy. That chemical potential energy is converted into electrical potential energy of the charge carriers. As the charge carriers move through the wire, they don't lose any potential energy. In reality, they lose a little bit, but we ignore that. It's negligible. When the charge carriers move from one side of the resistor to the other, they lose potential energy. And the charge carriers on this side of the resistor have less energy than they did on this side of the resistor. Energy can't be created or destroyed. Where does that energy go? The energy is converted from electrical potential energy into the resistor. What does the resistor do with that energy? This depends on what the resistor is. In a simple example, this resistor is an incandescent light bulb, and so the resistor heats up and it produces lights. Another example, this resistor could be your dryer, which is drying your clothing. The energy used in the resistor would be your dryer rotating and drying your clothes. When it says which one of these resistors dissipates the most power, when they're talking about dissipating power, they're talking about converting energy from electrical potential energy into energy used by the resistor. Power is energy per time. You need to constantly supply energy per time in order for your light bulb to keep shining, or for your dryer to keep working, or for your computer to keep working, or whatever the resistor may be. If I were to open this circuit and current stops flowing, then and these resistors were light bulbs, then the light would turn off and you'd be sitting in the dark. If this resistor was a dryer drying your clothing and I opened the circuit, the dryer would stop working. You'd have to walk around with wet clothes all day. The question is, which one of these resistors dissipates the most power? Power has units of energy per time. Which one of these resistors dissipates the most energy per time? In a series combination, the current is the same in both one of the resistors. The formula for power, which is energy dissipated per time within the resistor, is I squared times R. Because the current in a series combination is the same, and we said that R1 is larger than R2, then the power dissipated in resistor 1 is going to be larger than the power dissipated in resistor 2 when you're in a series combination. In a parallel combination, power is still I squared R. This is the formula for power. You can use Ohm's law and replace I with V over R. Therefore, power can be written as V squared over R. Power 1 is V squared over R1. Power 2 is V squared over R2. And because R1 is larger than R2, then power 2 is going to be larger than power 1. I left off the 1 here. So what is the takeaway concept? The takeaway concept is when resistor 1 is larger than resistor 2 in a series circuit, more power is dissipated in resistor 1 than resistor 2. If resistor 1 is larger than resistor 2 in a parallel circuit combination, then more power is dissipated in resistor 2 than resistor 1. And one reason for this is because more current will flow through resistor 2 than will flow through resistor 1. Here's the second conceptual problem I'm going to discuss. Bulbs being light bulbs, 1, 2, and 3 in the below schematic are identical. Part 1. Rank the brightness of the light bulbs from most bright to least bright. This is a schematic diagram. There's a battery. There's a light bulb 1, light bulb 2, light bulb 3. They're identical, so they all have the same resistance, which I've labeled R1, R1, R1. Now the question is, which one of these light bulbs is the brightest? And that's saying which one of these light bulbs will dissipate the most power. Question 2 asks, if light bulb 3 is replaced with a wire, does light bulb 1 get brighter dimmer, or stay the same? If I were to take light bulb 3 and replace it with a wire, does the power dissipated in light bulb 1 become more or less or stay the same? You may want to pause the video now and think about this. The answer to part 1 is that light bulb 1 will be the brightest and both light bulbs 2 and 3 will be equally bright. This is because the battery draws current. All of the current will go through light bulb 1, and then once the current gets to this junction, it's going to split up, and half will go through light bulb 2, half will go through light bulb 3. The reason it splits up equally is because the resistances are all the same. Power dissipated is equal to I squared R. I is larger for light bulb 1 than it is for light bulbs 2 and light bulbs 3, and therefore 1 is going to dissipate the most power, and the power dissipated by 2 and by 3 are equal. Light bulb 1 is going to be the brightest. Both light bulb 2 and 3 will be equally bright, but they'll be less bright than light bulb 1. Now let's discuss question 2. If light bulb 3 is replaced with a wire, now this is what the schematic looks like, and you have a resistor in parallel with a wire which has zero resistance. Essentially, in reality, it doesn't have zero resistance, but the resistance of the wire is much smaller. Parallel combination of a wire and a resistor is just a wire. And so therefore, this circuit diagram, the equivalent circuit is this picture on the right. The equivalent resistance is smaller. If you replace light bulb 3 with a wire, the equivalent resistance of the circuit is smaller than it would be if there was no wire there. Therefore, more current is going to be drawn from the battery, and light bulb 1 is going to be brighter than it would be if there were not a wire where light bulb 3 was. Also notice that light bulb 2 won't even light up at all, because all of the current will go through light bulb 1 and then it will split, and all of the current will go through the wire. So light bulb 1 won't light up, and light bulb 2 will be brighter. It may not be much brighter. It's going to be brighter. Here's the third and final conceptual problem I'm going to be discussing. This is a multiple choice question. It says, in the below schematic diagram, is the equivalent resistance between points X and Y less than 180 ohms, greater than 180 ohms, cannot be determined because other resistance values are not given. This problem shows point X and point Y. There's a resistor of 100 ohms, a resistor of 80 ohms, and then 3 resistors which are unspecified. They can be any value. There's no restriction on the value of these 3 resistors. And the question is the equivalent resistance going to be greater than 180 ohms, less than 180 ohms, or it can't be determined? You may want to pause the video and think about this. The answer is A, less than 180 ohms. And the reason is because this 80 ohm resistor can be written as a parallel combination with these other resistors. I'll give an example where I assign values to RA and B and C. And anytime you have resistors in parallel, the equivalent resistance is smaller than any one of the individual resistors. That's the main concept. Let's assign random values to RA, RB, RC and demonstrate this. This is the 80 ohm resistor, and I've just assigned 500 ohms to RA, 100 ohms to RB, and 200 ohms to RC. What I notice is these 2 resistors are in parallel, so I'm going to add them up in parallel and get an equivalent resistance. 1 over REQ equals 1 over 100 plus 1 over 200, and that tells us that the equivalent resistance of these 2 parallel resistors is 200 by 3. Therefore, I can redraw this schematic. The 80 ohms is here. Here's the 500 ohms, and then I replace these 2 with 200 over 3. The 500 ohms and the 200 ohms are in series, so I can add them up in series. And now what I'm left with is an 80 ohm resistor in parallel combination with another resistor of 1700 by 3. The key concept is anytime you have 2 resistors in parallel, the equivalent resistor is always going to be smaller than any of the individual resistors in parallel. Therefore, the equivalent resistor has to be smaller than 80 ohms. The equivalent resistance has to be smaller than 80 ohms. We're going to add these 2 resistors up and show that. 1 over REQ equals 1 over 80 plus 1 over 17 by 3. That's 1 over 80 plus 3. 1 over 1700 by 3. That's 1 over 80 plus 3 by 1700. And the equivalent resistance is 70.1 ohms, which is smaller than 80 ohms. The key takeaway point is whenever you have resistors in series, it doesn't matter how many there are. There could be more than 2. the equivalent resistance is always smaller than any of the individual resistors. Therefore, the answer to this problem is less than 180 ohms, because you're going to have a 100 ohm resistor in series with a resistor that's smaller than 80 ohms,